I left you with a question, and here was the question. The observed rotation of 2 grams of a compound in 50 mils of a solution, it told you how you made your sample, in a polarimeter tube, 50 centimeters long, is 13.4 degrees. What is the specific rotation? Okay, so I showed you the equation that we had to use for this, didn't I? I told you that specific rotation was the observed rotation divided by the length of the tube times the concentration of the stuff that you're putting in the tube. We just have to make sure that our units are proper. All right, so for concentration, they make us love the unit grams per mil. That's really what we're after here. And in this question, we have 2 grams of substance divided by 50 mils of solution, right? In a total of 50 mils. So the only thing that I have to do in order to get the proper value that I need for concentration is I need to go through and take 2 divided by 50 and hit enter. And this gives me 0.04. So that is the value that I'm going to use for C in this equation. 0.04. There's my concentration. 13.4 degrees is what I saw. 13.4 degrees is what popped out on the instrument when I ran it. So that is the observed rotation. 13.4 needs to go up on top. Next, down at the bottom, we need L, length. The problem is that length needs to be in decimeter, not in centimeter. There's an issue. We need to convert. How do we do it? Well, you can move decimals if you remember what to do, but I'm going to review dimensional analysis just for fun. You know, back in the day in general chemistry, when they introduced you to the prefix and said, this is what centi is, and this is what milli is, and this is what deci is. That's what I'm getting ready to do. So I'm going to take the given, which is 50 centimeters over 1, and I need decimeter, but that's a different prefix. So in order to go from one prefix to the other prefix, I kind of have to go to the base unit first. So centimeter on top, centimeter goes on the bottom, and we go to meter. How many centimeters are in a meter? Centi is century. Century is 100 years. There's 100 centimeters in a meter. Now we have meter on top. We need meter on the bottom. I need to go to decimeter now. That's the prefix that I need for the equation. So in 1 meter, how many decimeters are there? Well, deci is decade. Decade is 10. So I'm going to pull the calculator back up so you can follow me. So I'll take 0.04 and I'll get rid of that. That was my concentration number. And here with the length, I'm going to take 50. I'm going to divide it by 100. And then I'm going to multiply by 10. Notice I left off all the ones. That's normally what I do. Anything multiplied by 1 is that number. Anything divided by 1 is that number. And then I hit enter. And this gives me a 5. So the length of the tube in decimeters will be 5 decimeters. And those are the values that I need to plug into this equation in order to solve for specific rotation. I work the bottom first. Okay, so 5 times 0.04 equals 0.2. So that means I need to take 13.4 and divide it by 0.2. Order of operations here, folks, right? Otherwise, if you key this all into your calculator in one step, it's going to take 13.4 divided by 5 and then multiply by 0.04. And that will probably give you a different answer. That's not what needs to happen here. L and C needs to be multiplied together first. Order of operations. That's why I said work the bottom first. So 13.4 divided by 0.2, and that will give me a 67 for an answer. So 67 is the specific rotation for this set of data. Based on this concentration, based on this polarimeter cell length, maybe not ideal textbook value, but once I correct for that and put it into this equation, I'm going to get a specific rotation of 67, which hopefully means that if I go to a textbook value and I look up this specific rotation for this compound, I hopefully will get something very close. Right? This is like boiling point. It's like melting point. It's like density. These values are very specific to those particular compounds. Now, we have another issue. If you were okay with that, that's great. That's great. Wonderful news. Wonderful. You'll be able to ace those questions without a problem. But we do have a problem, because this equation that we just solved for has a big assumption. We assume something. And what we assume is that I'm working with a pure compound. No contamination. No other enantiomer present either. So the issue here is that sometimes that's not the case in a laboratory environment. Sometimes we work with these compounds and they are not enantiomerically pure. They are mixtures. They are mixtures of positives and negatives. So if I have a compound that is a mixture, how do I handle this? Well, we can do another calculation. I know, you probably don't want to hear that. I don't either. But there's another calculation that we can do. This is called enantiomeric excess. That means there is a mixture, but one of these are going to outweigh the other. So I actually get a value. I get a value from the polarimeter, an observed rotation, and I write down that number. But I know that this is not a pure compound. I know that this is a mixture of the positives and the negatives, and we're trying to get a percentage here. I mean, is it 60-40 split? Is it 70-30 split? Is it 75-25 split? Is it 90-10% split? That's what we're after with this equation. How much of one do I have versus the other? And this is how we do it. To calculate enantiomeric excess, I'm going to take the observed rotation, alpha, straight from the instrument. And I'm going to divide that by the specific rotation of the pure enantiomer. Positive, negative, whichever one that's used, that's the one I'm going to go for. And then we multiply that by 100%. That's it. But it's tricky. Let me show you why. So let's say, for example, that I have a compound, okay? And this compound I put into the polarimeter, I got an observed rotation, and I ended up getting a 9.2 for that observed rotation. How much of one do I have over the other based on that value? In order to answer that question, I need to know a little bit about the pure, right? This is the mix. There's positives and negatives both mixed together. I've put it into a polarimeter cell. I ran it on the instrument, and I got a 9.2. Well, what do I do with that number? If I want enantiomeric excess, because I know that this is a mixture, then I need to know the specific rotation of the pure compound. And folks, this is a positive value. So I'm probably going to pick the one that gives me the positive enantiomer, right? The one that rotates light right-handed. So the problem hopefully will give me this value. If not, and I'm in a laboratory, then hopefully I can use something like Wikipedia or something like the Merck or the CRC to figure out what this pure specific rotation is supposed to be. And let's say that that number is supposed to be a positive 23.1. Okay, I'm getting closer. My mixture is 9.2. The pure, the enantiomeric pure compound should be a 23.1. So that equation tells me I just need to divide them, and I multiply by 100. How hard can this get, right? Psh, why am I even in this class? This is pretty easy. So let's take 9.2 divided by 23.1, and then we'll times it by 100, and I get something, let's round it off. Two significant figures. Let's go to 40%. Keep it easy. What does this mean? This means that it is 40% in enantiomeric excess. This is where people have problems. The equation is simple to solve. And folks, I don't even want you to memorize this equation. I'm going to give it to you. I'm going to give it to you on a test. You just got to know how to use it. 9.2 divided by 23.1 times 100. How hard can it get? This is the next part that's the tricky part. You have to understand that 40% is excess. I have 40% more of one than the other based on that value. Okay, well, what's the other 60%? This is where the trick happens. The other 60%, this is a racemic mixture. We've talked about the word racemate. We've talked about the word racemic. A racemic mixture is a mixture that's basically split down the middle. It's equal. It's equal on the positive side and it's equal on the negative side. Oh, okay. So what this means is that if 60% is racemic, out of that 60%, 30% of it is going to be the positive version and 30% of it is going to be the negative version. This is the positive version that we ended up with here. Positive 9.2. Well, that 40% has to be added on to that 30%, folks, and this is going to give me a 70% positive and a 30% negative. That's the trick. That's the part that people forget about. They solve the equation and they say 40% excess. Okay, great. Now what do you do with that number? You better not give me 40% because that's going to be a wrong answer. That's 40% extra of one over what was already there. That's what that means. So the other part, that 60% part that you didn't account for, that is a evenly split part. That 60%, split it down the middle, 30-30. If that was 80 and 20, 20% excess, 80% racemic, you split the 80 in the middle, 40-40. You always split the other half in half. And in this case, 60% divided by 2 is 30. So I have 30% positive from the racemate mix. And then I have 40% more of the positive from the calculation. And I need to combine those two values together. So in total, 70% represents the positive version, and 30% represents the negative version. That's the part that people forget when it concerns these enantiomeric excess problems. All right? So again, if I solve this equation and I get a 10% here for excess, that's great. But the other half of the story, you have 90 that is a racemate, an equal mix. That 90 is split in half, 45 and 45. So I'll take the 45 and I'll add it to the 10 that was here, and that will give me 55% in total. 55, 45. That is how we solve these problems. All right. Something else I've also said before, you can have more than one chiral center. And here's an example of that. Here's a molecule, and it looks like this is not a chiral carbon, 3 hydrogens. This one's not a chiral carbon, 3 hydrogens. These two would be questionable ones with the asterisks on them. So this carbon has a hydrogen and a methyl group and a chloro group, and then this ethyl group with an OH. 4 different carbons. Yes, that is a chiral center. On the right-hand side, this carbon has a hydrogen, an OH, a CH3, and then this 2-piece with a chlorine on it. Yes, there are 4 different groups on that carbon as well. We have 2 chiral centers. Okay, well, if we have more than one chiral center, how many stereoisomers can we actually get from this thing? Well, we have an equation to make this process easier. It's 2 to the n power. And n is going to represent the number of chiral centers that you have. And in this case, there's 2. So 2 to the 2nd power, because there's 2 of them. Well, 2 times 2, 4. 2 squared is 4. I'm going to have 4 stereoisomers with this particular compound. How do I get those 4? Well, keep in mind, this first one will give you an R and an S form. This next one will give you an R and an S form. So if I combine these options together, R, S, R, and S, I can have an RR, an RS, an SR, and an SS. There's my 4 options. As you increase the number of chiral carbons, folks, the number of stereoisomers drastically increase as well. If there were 3 of them, that's 2 to the 3rd power. 2 cubed. 2 times 2 is 4. 4 times 2 is 8. If there were 4 chiral carbons, which is very easy in the world of organic, well, that's 2 to the 4th power. 2 times 2 is 4. 4 times 2 is 8. 8 times 2, 16. It doubled. You can see how complicated these molecules can become. If you wanted to draw out those versions for that particular compound that we just showed, here are your 4. 1, 2, 3, and 4. These are all perspective formulas. I know that because they're solid wedges and they're dashed wedges. And they're also drawing them in a way to give me the staggered conformer. You see that in big bold red. The reason is because this is the most stable form of the molecule. We've talked about this. These are alkanes. That's a single bond. And this single bond is freely rotating. And it will freely rotate and twist and turn until those groups are staggered from each other. And that's the preferred method it needs to be in. And then off of each one of these carbons, there's some 3-dimensional aspects to it that I need to keep in mind. And now we know that these 3-dimensional points and directions can give me left-handed and right-handed forms. What you're going to see here is isomers number 1 and 2 and isomers number 3 and 4. These are stereoisomers. 3 and 4 are stereoisomers. Stereoisomer just basically means a different way that we can draw the molecule and point it in a different direction. That's all that means. 1 and 2 are enantiomers. Okay? So with 1 and with 2, they are enantiomers, meaning that they are mirror images. You can almost see that, right? If I did the dotted line here, and I take this molecule and I flip it, well, my CH3 goes right-handed, my chlorine goes right-handed, my hydrogen goes right-handed. Then the hydrogen here goes to the left, my OH group goes to the left, my CH3 goes to the left. There you go. There's the mirror image. That is called the enantiomer. Just, again, confirmation of the term that we used back in the day. 3 and 4, same kind of deal. 3 and 4 are stereoisomers. 3 and 4, though, are also enantiomers, meaning that they are mirror images of each other. So if I took this molecule and I flipped it, again, methyl goes right-handed, hydrogen goes right-handed, chlorine goes right-handed, and then I flip it the other way. My hydrogen is left, my OH is left, and my CH3 is left. Now, with that said, there is another term, and it's going to be confusing. I'll just go ahead and warn you, that we can also bring into play. Stereoisomers, great. Everything's a stereoisomer so far. Cis and trans are stereoisomers. E and Z are stereoisomers. R and S are stereoisomers. Enantiomers are a little bit more specific. Enantiomers are mirror images. Okay? But there is another term. What do we call something like number 1 and number 3? How are they related? Or how is number 2 and number 4 related? Or how is number 1 and 4 related? Right? I mean, here I see 4 compounds. They are related in some form or fashion. They might not be brother-sister, but they might be cousin. And we've been talking about brother-sisters. We've been talking about mirror images. Very, very close relationship. But 1 and 3 could be cousins. Part of the same family. Same kind of structure. They're just a little different, right? If I look at the difference between 1 and number 3, are they mirror images? The answer is no. They're not mirror images here. H, OH, CH3 are all on the same side. CH3, CLH, they're all over here on the same side. So we did not flip them. Okay, well, if we didn't flip them, then what is the difference? Look at the orientation. Chlorine is pointed backward, and in here, chlorine's pointed towards you. Hydrogen is pointed towards you here, and on this one, hydrogen's pointed away from you. So they literally took these 2 atoms and they just switched them. That's what they did. Everything else kind of stayed the same on that side. They just pointed them in a different direction. They didn't take a mirror image. They didn't flip them as far as flipping it to make a mirror image with. They just switched the location of the 2 atoms. Oh, it's an isomer then, isn't it? Isn't that the definition of an isomer? It is. These are stereoisomers. So I'm probably going to see the word stereoisomer involved in this new term. And we do. If I look over on the right-hand side, H is pointed back, H is pointed back. The OH is pointed toward me, the OH is pointed toward me. And then here the CH3 is on the flat bond and the CH3 is on the flat bond. Folks, this is all that they did. To go from number 1 to number 3, the only thing that happened was they switched the location of the hydrogen and the chlorine. And that was all. That was all. So these are stereoisomers. Check. They are stereoisomers. In the stereoisomer, there's plenty of categories. Are they enantiomers? No, they're not enantiomers. The reason is because they're not mirror images. We didn't literally flip them around. So there's got to be another term to describe these. Something that's the same molecule, it's an isomer, they're stereoisomers, they're connected in the same way, but they just point in different directions. But yet they're not mirror images. And what we call that is a diastereomer. I see stereo for stereoisomer. I also see mer for isomer. They just leave out the word iso. I wish they would leave it in, stereoisomer. I don't know why they couldn't, but they just decided not to. So this confirms that they are stereoisomers, which is good because they are. Same connections, same carbons, same hydrogens, same oxygens, same chlorines, just connected and pointed in a different direction. But they put the word dia out in front, and that is what that means. That is that definition. If they are not enantiomers, they probably are diastereomers. If you don't flip them and do a mirror image, but yet it's the same molecule with the same number of everything and they're just pointed in a different direction, then these, by definition, are called diastereomers. They are not mirror images, and they are not identical. So if you really want a true definition, this is how they define it. They will say a diastereomer are stereoisomers that are not enantiomers. And a lot of people are just so confused when they see this definition for the first time, because we slap you with this definition of enantiomer first, and we might not really stress that enough, and then we turn around and we change it again, and we give you a term called diastereomer, which is by definition including a word that you've just learned. So in a way, we're giving you new vocabulary, and then we're giving you a new vocabulary term based on the recent vocabulary that we told you to use, that we've only given you a couple of minutes to get acquainted with. And that's where people begin to struggle with diastereomer. But folks, that's all that it is. Diastereomers are just same molecule, same connections as far as carbons, hydrogens, oxygens, and everything else go in the molecule. They're just pointed in a different direction, but yet they're not really true mirror images of each other. So that is the term that we use for that purpose. All right, so that's where this video is going to stop. The next video we'll pick up from there, and we'll kind of keep trucking on through the world of stereoisomers.